Hey everybody, Mr. Brown here, and in this presentation we are going to cover everything that you're going to be expected to know from Chapter 5. It won't be everything, so if you just stick to what we cover in this presentation, that should be everything you need to know. Most of it comes from sections 5.1 and 5.2, so feel free to follow along and figure out what it is you need to know from Chapter 5. In Chapter 5, we see some more advanced theories of atomic bonding. In the previous chapters, we discussed VSEPR theory, how molecules are shaped, but we didn't really address how the bonds themselves are formed, and that is what Chapter 5 is all about. The first theory of bonding we're going to cover is the valence bond theory, and it is one way to describe how electrons are shared to form covalent bonds. In the valence bond theory, the linchpin of the valence bond theory is that half-filled electron orbitals overlap to form fully filled orbitals, and this is what we call a covalent bond, is when two half-filled electron orbitals from two separate atoms overlap and share those electrons in order to fill those orbitals completely. We will see that when orbitals overlap head-on, we call the bond a sigma covalent bond, and when p orbitals overlap side by side, we are going to call that a pi covalent bond, and we'll see some drawings and examples of those on the next couple of slides. Here we have the simplest covalent bond we can model, and that is the covalent bond that forms the H2 molecule. When two neutral atoms of hydrogen, which both have one electron in their 1s orbital, come together and share those electrons into each of one of those 1s orbitals. Those orbitals overlap, as you see in the picture there, and they overlap head-on in a line that connects the two nuclei, and we call that a sigma bond. This is the simplest example of a covalent bond we can model. We can also imagine a sigma covalent bond as two p orbitals overlapping head-on. We can see here in the bonding between two fluorine atoms to create the molecule F2. We have two fluorine atoms, both which have one 2p orbital that is half filled. They have two 2p orbitals that are fully filled, but each have one a 2p orbital that is half filled. It only has one electron. If those two atoms bring that p orbital close together head on, they can overlap according to valence bond theory and form a covalent sigma bond to fill that orbital up. And again, because of the head-on overlap, it's referred to as a sigma bond. Here we have a third example of a sigma bond that is formed between the 1s orbital of a hydrogen atom and the 3p orbital of a chlorine atom to form the bond that forms the molecule HCl, or hydrogen chloride. The 1s orbital of a neutral hydrogen atom is half full with only one electron, and the 3p orbital of the chlorine, one of the 3p orbitals of the chlorine atom, of a neutral chlorine atom, is half full. If those two orbitals are brought close together and they overlap head-on, as you see in the illustration down here below, we refer to that as a covalent sigma bond. So far, we have seen how overlapping simple atomic orbitals works well for diatomic molecules to explain how bonding occurs. However, as molecules add a little bit of complexity, for example, here in our methane molecule, which has the formula CH4, our current version of the theory falls apart a little bit. If we investigate the electron orbital diagrams of the neutral carbon and hydrogen atoms, what we might find, or what we might expect, is that what we see is that in order for our current bonding theory to work, we would overlap and
one s orbital with one of the 2p orbitals, another 1s orbital with one of the other half-filled 2p orbitals, and then we're out of half-full orbitals with which to overlap. We might suggest that each of these s orbitals overlaps with a 2p orbital, but that would only result in 3 regions of electron density, which would not lead to the tetrahedral shape of the molecule. So one of the theories needs to be refined in order for it to agree with experimental evidence. And our experimental evidence that we have up to this point really points strongly to the tetrahedral shape of the molecule. So it's the valence bond theory that needs to be updated. So it was proposed that what atoms do is that they mix some of their orbitals in order to form new, more half-filled orbitals with which to bond. We say that these orbitals have been hybridized, and very often they are mixes. In the case of methane, they are mixes of the s and p orbitals. The new orbitals will have characteristics of the orbitals that was used to hybridize them, and it's important to note that the number of orbitals that get combined is the same as the number of hybrid orbitals that are the result of the process. Here we see some important notes about hybridization that we would do well to remember going forward. Hybrid orbitals only exist when atoms bond to form molecules. They have different shapes than their atomic orbitals they are made from. However, they often share many of the characteristics of each. A set of hybrid orbitals is generated by combining atomic orbitals. The number of resulting hybrid orbitals is always the same as the number of atomic orbitals that are combined to form them. All resulting hybrid orbitals of a combination have the same energy. Hybridized orbitals always overlap head-on to form sigma bonds, and leftover unhybridized orbitals overlap side by side to form pi bonds. On this slide, we see the Lewis dot diagram for the BeCl2, the beryllium dichloride molecule. It's important to note right away that beryllium is one of the atoms that can satisfy the octet rule by simply having 4 electrons, as we see in the 2 single bonds that it shares. And so we are going to investigate how those sigma bonds are made. If we look at the ground state electron configuration of beryllium, we see that it has 1 full orbital, the 2s orbital, and 3 empty 2p orbitals. Our bonding theory says that we need half full orbitals in order for bonds to occur. And while the chlorine has some half full 3p orbitals, beryllium has no half full orbitals. So in order to make half full orbitals, 2 of them specifically, because we see 2 bonds here, he's going to have to hybridize 2 orbitals. So he will hybridize a 2s and a 2p into 2 sp hybridized orbitals. He will also still have 2 leftover unfilled regular p orbitals that are not hybridized. These 2 sp orbitals will have some characteristics of s and some characteristics of p that we see here, where one of the lobes becomes smaller, and they will orient themselves at 180-degree directions from each other. These sp orbitals will then head-on overlap with these 3p orbitals, as we see in the diagram here, to form the sigma bonds that we see in the Lewis structure. Here we have the description of the bonding in the BH3 molecule. Boron only needs 6 valence electrons in order to satisfy the octet rule. And so if we look at a ground state configuration of boron, we see that it has 1 full 2s orbital and 1 half full 2p orbital. But in order to form the 3 bonds that we see in the Lewis structure, he needs 3 half full orbitals. In order to make 3 half full orbitals, he's going to combine one of the 2s and 2 of the 2p's into 3 sp2. sp2 because it was made with one s and two p's. He leaves one of the p orbitals unhybridized. This one here is left unhybridized and empty. And then he can form those three bonds. Each of these sp2 orbitals can overlap with the 1s orbital of hydrogen in order to form the 3 sigma bonds that are needed for the Lewis structure seen here. We show again here with the methane molecule how 4 regions of electron density, or 4 sigma bonds, will require the use of 4 different orbitals, 1 of the s's and 3 of the p's, in order to form 4 sp3 orbitals. In some of our central atoms that break the octet rule and go higher than 8 electrons, it is necessary to involve the d orbitals that are involved in the bonding. In the case of PCl5, there are 5 sigma bonds around the phosphorus atom. So in order to get 5 orbitals, half-full orbitals in which to bond, he has to take his 3s orbital, 3 of his 3p's, as well as 1 of the 3d orbitals in order to make 5 sigma bonds. The 5 half-filled orbitals that result are called sp3d because that's what they are composed of. Finally, on this slide, we show that for the SF6 molecule, in order for the sulfur atom to form 6 sigma bonds, he has to involve 6 orbitals in order to produce 6 hybridized half-full orbitals. Those 6 orbitals are 1 of the s's, all 3 p's, and 2 of the d orbitals. We call these hybridized orbitals sp3d2. Now we can discuss how multiple bonds are formed in molecules. We see a Lewis structure for ethylene, C2H4, in which 2 carbons share a double bond. In order for these 3 regions to be formed, in order for these 3 sigma bonds to be formed, then the carbon needs to hybridize 3 orbitals. So he will hybridize 1 of the s and 2 of the p's. This leaves us with 3 sp2 orbitals and 1 half-full regular p orbital that was left unhybridized. That unhybridized orbital sticks up and down from the atom of the nucleus, while the 3 sp orbitals orient themselves as trigonal planar orbitals around the nucleus. One of these orbitals overlaps with the other carbon here in a sigma bond. The other 2 orbitals overlap with the 1s orbitals of hydrogen atoms in order to form further sigma bonds. The pi bond, the double bond seen here, is formed by the overlap of these 2 half-full regular p orbitals, but they do not overlap head-on. This side-by-side interaction above and below the nucleus is what is referred to as a pi bond. Triple bonds work the same way as double bonds. However, in triple bond hybridization, only 2, an s and a p orbital, are hybridized. This results in a linear arrangement of those hybridized orbitals, with the unhybridized half-full p orbitals sticking up to the tops and the sides of the nucleus. Then you have 2 overlapping bonds forming between the 2 carbon atoms, the result of which is a triple bond. If you can identify how many regions of electron density are around the central atom, then you can easily consult this chart and determine what the hybridization of that central atom is. Simply determine how many electron groups are around that central atom, and then look over here and you will be able to determine what orbitals it used to hybridize in order to form that structure.